Hello, we are Biomedical Engineering Team 9, and our project focuses on an external bone fixation device for rat femur model. In bone tissue engineering, it is very common to use a long bone of critical size defect to test the efficacy of scaffolds meant to regenerate bone. This is most commonly done by placing the scaffold in the defect of a rat femur and studying the bone growth and healing over time. Common problems stem from mechanical properties of scaffolds that rarely match that of cortical bone, and these scaffolds cannot support the loads they undergo while implanted in the rat femur. This is mitigated using fixation devices that hold the femur and maintain the defect while the bone heals. To avoid using multiple surgeries that are necessary when using an internal fixation device, an external fixation device may be used. The most popular commercially available external fixation device shown here uses pins that are screwed on either side of the defect and external stiffness bar to maintain the defect.
Our design focuses on ease of use and reduced cost. A more intuitive device that requires minimal training will dramatically reduce costs associated with performing these complex procedures and will allow greater accessibility for researchers studying long bone defects in rat femur models. Our design is sterilizable and allows for an adjustable stiffness, both of which contribute to the device being reused, further reducing consumer costs. Additionally, our design is non-degradable and biocompatible to prevent an immune response in the rat. To prevent bone fractures commonly caused by current devices which use pins, we developed a design that features clamps that firmly grip the femur to ensure stability without needing to screw pins into the bone.
This slide shows the external pieces of our fixation device. The top piece, the top image, and the bottom piece, the middle left image, were both 3D printed out of ABS. Each piece has 4 holes that are 2 millimeters in diameter. The dimensions of the top piece are 12 by 21 by 2 millimeters. The bottom piece has the same length and width and a thickness of 3 millimeters for added support. We also have 3 pairs of adjustable stiffness components that are also 3D printed with ABS. Pieces are easy to assemble and remove because the stiffness can be adjusted by adding or removing a pair of elements. 100% stiffness has all 3 element pairs attached. 75% stiffness has 2 element pairs. 50% has 1 element pair, and 25% stiffness has no elements attached.
Shown here is a picture of our final assembled device. There are 4 clamps in alternating directions. Each clamp is designed with 2 prongs, with the screw component acting as an additional fixation against the femur. The clamp component is composed of a pin, screw, and prongs made of stainless steel. The screw moves up and down to adjust the tightness of the clamp on the bone. Each screw is 2 millimeters in diameter, 30 millimeters in length, with a 0.4 millimeter thread. Here is a 3D printed prototype of the device shown to scale.
Due to lab access limitations, our group was only able to discuss and outline anticipated testing, expected outcomes, and reactions to different testing scenarios. The planned procedures and testing started with converting the scans of the rat femurs to STLR files for device integration. As you can see below, we were able to accomplish this remotely from the lab. We also intended on executing compression and tension testing, as well as the 3-point bending test on both the femurs and the device itself. Based on reviewed literature, we expected the stiffness and failure load to range around 315.6 newtons per millimeter and 175.4 newtons respectively. Using values produced during these tests, we would be able to calculate the longitudinal Young's modulus of the rat femur. This value would serve as a benchmark for our device to ensure that the device would maintain structural and functional stability during use. If our device fell below any of the produced standards, material or device modifications would be investigated.
In conclusion, we were successful in designing and fabricating an external fixation device, but unfortunately, we were unable to conduct any experiments. And since we were unable to perform any tests and collect any experimental data regarding our device, the next step in the process would be testing, as was just mentioned by Ian. The methods of testing that we would use for the characterization of our device are compression and tension testing with the Tenius-Olson machine, as well as a 3-point bending test, thereby elucidating the reliability of our device. And depending on these results, the next step would be to either continue forward with in vivo testing using the device to test bone scaffolds and large bone defects of rat femurs, or to address and fix any device issues before moving forward.
Thank you to Dr. Kumbar, Sarah, and the UConn BME department.